We're going to talk about 4 major periodic trends. Your book will go into them into more detail if you want to read up on that or whatever. But we're going to talk about 4. Listen. Atomic radius is the radius of the atom. Do you think we could just get out a ruler and measure the radius of the atom, right? Not going to happen. So the radius of the atom is measured by basically this kind of formula. It's half the distance between the nuclei of identical atoms. Okay, so let's think about a couple things with this. Half the distance between 2 identical atoms. Why do they have to be identical atoms?
Because then they have the same radius.
Yeah, then they have the same radius. Exactly. So half the distance between identical atoms. The reason we deal with that rather than finding a defining edge and trying to measure the distance from the nucleus to the outer edge is that our electrons are in constant motion, right? Our electron orbitals are not clearly defined edges, right? Electron orbitals are like pockets where electrons are located, but they don't have pocket edges, right? They're like just little zones, kind of. So it's hard to find where does our atom really end. And so we look at the distance between the 2 nuclei of an identical atom, of identical atoms, and then we take half the distance, right? That gives us an approximate atomic radius, right? Does that make sense how that works? They've got to be identical because if you've got an oxygen atom and a hydrogen atom and you try to take half the distance, right, we're not at an atomic radius. That's correct, right? So it's got to be 2 identical atoms. Okay, so I'm going to show you the trends always for an increase of the property. Basically, I'm always going to point you in the direction of an increase. Okay, so for atomic radius, we see atomic radius increase on the periodic table as we go to the as we go to the left, and as we go down. Okay, so it increases and it increases. Okay, and I know this is counterintuitive because it's backwards and down, but I want all the trends that you remember to be, they get bigger as they do this, right? Rather than trying to remember this one gets smaller as it goes here, blah, blah, blah. Okay, and then I'm going to talk about why this is the case. Okay, we see an increase as we go to the left, and we see an increase as we go down. So let's talk through why do we think our atomic radius increases as it goes down. It gets bigger, right? More specifically, what happens to the atom as it goes down a row on the periodic table? More electrons. And so specifically, what does it do? It adds an orbital or a shell, right? It adds another energy level. Okay, so let me write out kind of the explanation here. Okay. Adds another energy level as it goes down a row. On periodic table, right? I just abbreviated periodic table, PT. Okay, so it adds another energy level, or you could say shell, as it goes down on the periodic table. So that's an automatic and easy way for us to see, oh yeah, our atomic radius is increasing because we're adding a whole other shell to the outside. Agreed with that? So as it moves to the right, as it moves across the periodic table, we see the atomic radius decrease. Okay, as it moves to the left, it gets bigger. As it moves to the right, it gets smaller. So can you see a reason that atomic radius would decrease as you go to the right? Yeah?
Isn't it because there's more pole to the radius and the smaller?
Yes, there's more pole to the nucleus. So as you go to the right, it's all right, I know what you're saying. As you go to the right on the periodic table, you add a proton, right? with every new element, you add a proton. And what does that do to the positive charge of the nucleus? It increases. So as the positive charge of the nucleus increases, it pulls the electrons tighter, right? The pull gets stronger. And so the atomic radius decreases as you go to the right. So I want you to just think about bigger radiuses on the left and down, right? Smaller as you go. So what's theoretically our smallest atomic radius? The smallest is helium, right? Biggest atomic radius would be francium, right? Francium has 7 shells and only not one proton, but it's got 1 electron in its outermost shell. You think it really wants to hold on to that outermost electron? No, right? It does not care. It wants to get rid of it. Okay, so it's not pulling that electron all that tightly. Okay, so that's periodic trends. It adds another shell and then added positive charge or protons pull electrons in closer. So why don't we see if sodium has 1 more proton than fluorine, why is sodium's atomic radius greater than fluorine's? Why doesn't it pull it even tighter than fluorine does?
It has a greater positive charge.
It has to add another shell, right? That whole shell gives that radius just a bigger value. Okay? I'm going to see if your book has a table that we can look at or a graph with that. I can't really remember if they did. Okay, yeah, here we go. Okay. It doesn't have a table for this one, but we're going to look at it. Okay, so next trend that we're going to look at is called ionization energy. Any idea what that might mean? Yeah, it has to do with ions. Ionization energy. It's the amount of energy required to remove an electron from a neutral atom. So how much energy does it take to make it an ion, right? That's what we're looking at here. If we take an electron away, that gives it a positive charge, right? So how much energy is required to make this an ion? Okay, any ideas as to our trend with this?
The opposite?
Yeah, the opposite. Very good. Okay, so it's going to increase to the right and up, right? Because if they're holding on to their electrons tighter, it's going to take more energy to pull them away, right? As we pull those electrons tighter and tighter and tighter, it's going to be very difficult to pull them away. So ionization energy increases as we go up the periodic table and to the right. And so if you want to pull out your textbook and see a table with this, it's on page 331. If you can't see it, it's not that big of a deal. It just shows you really evident spikes in terms of the ionization energy. Okay? Okay? It shows us really evident spikes in ionization energy. So if you're looking at your textbook, what elements have those high spikes? Helium, neon, argon, krypton, xenon, and radon. What group of elements are those? The noble gases. And why would they have the highest ionization energy? They have... No, one more. 8. They have 8 electrons. They have 8. They're in group 8 or 18. They have a full shell, right? They're S2 and P6. They're full, right? So they take the most energy to pull an electron off, right? They have 2 electrons in the s orbital, 6 in the p orbital, which gives them 8.
Period is this way.
Group is this way. Period is this way. Period is like row. Yeah.
So then for this one, helium would be the largest.
Helium would have the largest ionization energy, right? It takes the most energy to pull an electron off of helium. Okay? Why do we see a decrease in ionization energy as we go down the periodic table? Why does francium have such a low ionization energy?
There's so many shells that like it's just so big.
That's right. Its outermost electron, it's got one valence electron in its outer shell, and it's 7 levels away from its nucleus. Right? It does not care. It wants to get rid of it. Right? There's 1 electron that's hanging on. It wants to get rid of it. Okay? So it doesn't take much energy at all. Okay? Electron affinity is essentially, there's the fancier definition for this, but essentially it's how likely an atom is to accept an electron. How likely an atom is to accept an electron. Okay, the real fancy definition for electron affinity is the energy change that occurs when a neutral atom obtains an electron. Okay, the energy change that happens when an atom takes on an electron. But the way to say it that makes the most sense, I feel like, is how likely an atom is to accept an electron. So where do we think we would see an increase in electron affinity? Group 7. Good. Group 7 or 17. So the trend for this is a little bit less clear, but I like to circle group 7 and I say it's going to increase as we go there. Right? It's going to increase as we get towards group 7. Because group 7 has 7 electrons. They only need 1. They're super likely to obtain an electron. Group 7 is like fluorine. Yep.
Do they increase going up or down?
Not necessarily. Electron affinity has a little bit of a different trend. If you look on page 333, electron affinity table, really the electron affinities are negative values. So fluorine and chlorine have high electron affinities, right? They have a large energy change, negative 300 kilojoules. And so you see a little bit of an increase kind of as you go down the periodic table, but not a whole lot. More so just I want you to focus on as you go toward group 7, you'll see an increase there. Okay? Does group 8, you think, have an assigned electron affinity number? No. Right, it won't accept an electron. Okay? Last one is electronegativity. Have we talked about electronegativity much? Not a whole lot. Anyone know what electronegativity is? Or how to describe? Not just negative electron. Okay, electronegativity. I'll give you the fancy definition, kind of. The ability of an atom in a chemical compound to attract electrons from another atom in that compound. Okay. The ability of an atom in a chemical compound is to attract atoms from another to attract electrons from another atom in that compound. So it's like I don't know how you want to say it. It's going to take or pull electrons to itself within a chemical bond. Okay, within a bond, it's going to pull electrons closer to itself. Okay, and so it kind of follows the electron affinity trend somewhat, kind of follows the ionization energy somewhat, but the increase in electronegativity points toward fluorine. Fluorine is the most electronegative atom, and each atom is assigned an electronegativity value. So each of them has a numerical value assigned to them about how likely they are to pull electrons from another atom. And fluorine has the highest electronegativity value. So the trend is just that it increases toward fluorine. That's it, right? To the right and up. Okay, and it kind of stops at fluorine. I'm going to give you that scale that has the electronegativity values because we use it for determining molecular structures. Okay, so I'll give you that here in a little bit.
So why does fluorine have the most?
Fluorine has the most because it's got 7 in its first shell. So it wants really, really, really badly to complete that first shell octet, right? Its energy level is closest to the nucleus and it's got 7. So it wants to complete its octet more than anyone else. Okay, chlorine wants to complete it, but it's in its second energy level, so it's not as concerned about it. Bromine's in its third energy level, so it's not really concerned about it, right? Elements that are close to fluorine, like these guys, oxygen and chlorine, they have similar electronegativity values, even though oxygen has 6 valence electron and chlorine has 7. So the ones that are close to fluorine like that, you'll have to just look at your table and see which one's more electronegative.
So when, like you keep saying like fill their octet and stuff, which I get, but
Mhm.
what happens to like group 3 through 12 with that? Is there like something that octet doesn't include those?
Right. They don't have a full necessarily octet. They would have expanded room because they're in the d orbitals. So they want to fill the 8 from the s and the p orbitals, but then in the d orbitals they have extra space. So they can have more than 8 around them and be okay with that. Okay. We're going to get into that as we look at structures, but yeah, that's a good question. Stephen, did you have a question? Okay. Are we good with periodic trends? Okay, perfect. This is getting into chapter 8. Which has to deal with chemical bonds, structures, all that kind of stuff. The title of the chapter is Bonding, General Concepts. Okay. So we're not going to follow necessarily the exact order that your textbook goes in. That's not really the order I like to teach it in, so I'm going to rearrange it a little bit, but it's still all in chapter 8. Okay, so if you're following along in your textbook, we're going to jump around a little bit. Okay, first of all, we got to talk about what is a chemical bond. Anybody? Yeah, go. Two atoms that are bonded together. So a bond or a chemical bond is a mutual attraction. That's important. Mutual attraction between the nuclei. Oops, I can't spell. And valence electrons, right? You're going to see me abbreviate valence electrons like that a lot because I don't have time to write out the whole thing. Okay. Of different atoms. About 3, but we're going to talk first about 2 specific types called ionic and covalent bonding. We know about ionic and covalent molecules based on naming. Can anyone remember what is an ionic molecule made of? Metal and a non-metal. Metal and a non-metal. So ionic is between metal. An ionic bond is between a metal and a non-metal, or a cation and an anion. And the thing that's specific about ionic bonds is that they trade electrons. They trade electrons, or specifically they give and take. Trade might not be the best word because they're not just swapping them, right? One of them's giving their electrons, the other one's taking electrons. Okay, so that's what happens in an ionic bond. Okay, I want you to just listen to this for a second. We're gonna see a visual with it eventually. But in an ionic bond, what happens is I give Allison my electron. What charge do I have now? All right, we're both neutral. I have a positive charge now. She has a negative charge. And so what do opposite charges do? Attract. So she's got a negative charge. I've got a positive charge. We hang out so closely now because of that attraction between charges, they call it a bond. Right? I give her an electron. She takes on a negative charge. I take on a positive charge. We're so close together because of that attractive full-on charge, right? The attraction between the charges, we call it a bond. That's an ionic bond. Okay? Covalent bond, however, is a sharing of electrons. Okay, and it happens between two non-metals. And this is sharing of electrons. Okay, so when you share something correctly, right, that means I put an electron out there, Allison puts an electron out there, we both get to count them as our own. Okay, so if I need one to complete my octet, she needs one to complete her octet, we both contribute one, now I get to use hers, she gets to use mine, we're good to go. Right, that's what a covalent bond looks like. Both of them get to count them as their own. That's what we're going to spend a majority of our time on in terms of structures, because drawing structures for covalent molecules is generally the focus. Okay? In a covalent bond, it's rare that they are shared, the electrons between the two atoms, it's rare that they're shared 100% evenly. What would be a time that you think electrons would be shared 100% evenly between two atoms? If the two atoms are what? Yeah, if they're the same type of atom. If we're both hydrogen atoms, we're probably going to share those electrons evenly, right? What'd you say? Oh, sorry. But if I'm fluorine and she is rubidium, who wants electrons more? I do, right? I'm fluorine. I'm most electronegative. So in a covalent bond, if there's uneven sharing of electrons, it is called a polar bond. Uneven. Oh, my stylus is about to. Yeah, this is a type of covalent bond. It's called a polar covalent bond, and it's an uneven sharing of electrons, right? Would mean even sharing of electrons. Okay? So you will use your Pauling scale that I gave you. Sorry, Ann, go ahead.
So polar and non-polar bonds are only in covalent?
That's right. That's right. And then, so covalent bonds are like a sliding scale. Okay? So a bond that is shared 100% evenly is called a nonpolar bond. A bond that's shared unevenly but still shared is a polar covalent bond. A bond that's shared so unevenly that we trade or give and take becomes an ionic bond. So it's a sliding scale between them, right? Nonpolar is we're sharing evenly, everything's good. Polar bond means we're still sharing, but it's mine, right? And then ionic bond is when we've separated ways, right? You've given, I've taken, whatever. Okay, so it's a sliding scale between those types of bonds. All right, let's see here. So if I wanted to look, for example, I'm going to give you some numerical ways to tell, is it ionic, is it covalent, or is it polar covalent, or whatever. Okay, so if we have an electronegativity difference, my stylus is just not happening. Electronegativity difference between 1.7 or greater. Greater than 1.7 would mean it's an ionic bond. If you have an electronegativity value difference between 0.3 and 1.7, it's a polar covalent bond. And if you have the difference between 0 and 0.3, that means it's a non-polar.
So if anything is greater than 1.7?
It's considered an ionic bond. That means they're not even sharing anymore. It's just a give and a take. Okay? And so you'll see that usually between metals and non-metals, right? Because those are ionic bonds. And so the separation between their electronegativities are so drastic that there's a total give and take. So if I wanted to look at a bond, let's say between, if I wanted to look at a bond between sulfur and hydrogen. Sulfur and hydrogen. Yes, I can. If I wanted to look at a bond between sulfur and hydrogen, what type of bond category would that fall into? Okay, sulfur and hydrogen. Okay, let's look at their electronegativity values and see. Because remember, hydrogen's technically a nonmetal, right? And sulfur's technically a nonmetal. Even though hydrogen's on the other side, still a nonmetal. So sulfur's electronegativity value, based on the table I gave you, that's called the Pauling scale. You can write that on the top if you want to. Pauling scale. Okay. Sulfur's electronegativity value is, anybody? 2.58, and hydrogen's is 2.2. So when we're looking at the electronegativity difference, we're just taking bigger minus smaller, right? It doesn't matter which element you subtract from the other, it's just bigger minus smaller. That gives us a 0.38 difference, which means it falls into the category of a polar covalent bond. Yep. This isn't a skill we'll have to do all that often, right? But it's just a little range of values that shows you the sliding scale between the types of bonds.
Which two do you subtract?
Sulfur's electronegativity and hydrogen's electronegativity, it's always bigger minus smaller. So it doesn't matter which element you subtract. Yeah, you're just looking for the difference between the two. That's it. Okay. Okay, we're feeling good so far? Types of bonds. Okay, the reason that atoms or molecules use a covalent bond is to complete their octet. Okay, and we know the octet means how many electrons? So the octet rule, atoms want 8 electrons. Okay, they want 8 outer electrons, and by using covalent bonding, they can share, right? If I have 7 and Allison has 7, I get to use one of hers, she gets to use one of mine, we count them as 8, right? So that's what we're talking about in terms of sharing, and they want to complete the octet rule. There are some exceptions to the octet rule. There's some elements that are okay with having fewer than 8 or more than 8. And so I'm going to show you just a couple of these exceptions now so you can kind of get them in your brain, but I can't tell you every single solitary exception, right? It happens. But I'm going to show you some that are general exceptions. Exceptions to the octet rule sometimes fall in group 3. So boron contributes 3 electrons to any bond, right? It's got 3 valence electrons. That's what it's bringing to the table every time. So it's okay if it only bonds with 3 things, or if it only has 3 electrons around it, because it only contributed 3, right? It's okay with that. So boron is a common exception in terms of having less than an octet, okay? And this will make more sense, I promise, as we start building the structures. But boron is an exception. And then sulfur, phosphorus, some of these guys down in this grouping right here can be an exception the other way. So they can have more than 8 surrounding them sometimes. Okay, and I'll talk more about that in a little bit, but I just want you to know Most things like to have 8 electrons surrounding it, but there are some exceptions. Okay? Let's look at now building our structures. And sorry, I know this is a lot today, but we still got a lot we got to get through. So we're going to look at building our structures. And so these are called Lewis structures. Lewis structures are 2-dimensional pictures of compounds. Okay, Lewis structures are 2-dimensional pictures of compounds. They call them Lewis dot structures, whatever, but these are they're Lewis structures. Okay, we're going to start really simple, and then we'll get into a little bit more complex. Okay, first thing that we're going to show you is the Lewis structure of an individual atom. Right, Lewis structure of an individual atom, and I'm going to show you a really basic bond. So fluorine has how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. Right? In general, electrons travel in pairs. Right? In general, electrons travel in pairs. So we set them up, basically when we're doing Lewis structures, we want to think about atoms, when we draw them 2-dimensionally, as having 4 sides. They've got 4 opportunities to do things. Because if electrons travel in pairs and we have 4 sides, that gives us 8 electrons. Right? So that's what we want. Fluorine only has 7. So this right here is the dot structure for fluorine. That's it. Okay? We're not going to use this very often, but it leads us to the next one. So let's say I have another fluorine, a green one, that also has 7 electrons. And these 2 fluorines need to bond. They want to bond. What type of bond would these 2 fluorines utilize? Covalent, right? They're going to share, they're the same type, so it's probably going to be a nonpolar covalent bond. So what's going to happen is they're going to come over, he's going to sit right next to him, and they're going to bond. Right? I don't know if you can see that green very well. In a chemical bond, there are 2 electrons. 2 electrons found in every bond. 2 electrons in a bond. That's really important. 2 electrons are in a bond. And so in this bond, we see between these fluorines, one of the electrons is from the green fluorine, and one of the electrons is from the purple fluorine, right? So that bond now can be utilized by both of these fluorines. And so as we go and count our electrons, we say the purple fluorine now has how many electrons surrounding it? 2, 4, 6, 8, right? He gets to count both. And then the green fluorine has 2, 4, 6, 8 surrounding it. So he gets to count both. So both of them are happy. Both of them have a complete octet. Does that part make sense? When you draw a bond, you don't have to draw the individual electrons. When you draw a bond, it's just a line between the 2. Okay? How are we feeling about how they form that bond? Okay? Is this easy? Okay. Make sure I don't have anything else I need to say. Okay. I'm going to give you now rules for drawing Lewis structures, and then we're going to jump in and start drawing them. Okay? So, I drew this one kind of backwards because we started with individual elements. I'm going to show you how I really think they should be done. So, steps for Lewis structures. Number 1, count valence electrons needed. Okay, so what I'm saying there is with my fluorine atoms, the molecule that I built was essentially F2, right? 2 fluorines bonded together. Yeah? And so each fluorine gave 7 valence electrons. So in total, my diagram should have shown 14 valence electrons in total, okay? So you're saying that doesn't add up to 16, right? Because they each had 8. But let's look at it again. Okay, each of them gets to have 8 surrounding it, 2, 4, 6, 8. 2, 4, 6, 8. But if you count total electrons, we've got 2, 4, 6, 8, 10, 12, 14. Right? So that matches the number of valence electrons we should have had. Right? Each one gave 7. We didn't bring in new electrons. We didn't take out any. We used exactly what we had. Okay, so step 1 is count valence electrons. So our valence electrons for F2 would be that. If I said count valence electrons for C3H8, let's count valence electrons for that. How many valence electrons does carbon have? One individual carbon has how many valence electrons? 4, because it's in group 4 or 14. So that means carbon gives us a total of 12. Each hydrogen gives us 1, and there's 8 of them. So in my structure, I would have to represent 20 electrons. That's what count valence electrons means. Okay? Step 2. Arrange atoms in the what we call skeleton. Arrange atoms in what we call the skeleton. And so that's just putting our atoms in the right spots without any electrons. Okay, and so there's some little like side notes for the skeleton. Okay, if carbon is present, it is the central atom. Okay, what's central mean? In the middle, right? It's in the middle. So if carbon is present, it is the central atom, always, no matter what. Okay? If you don't have carbon, so let's say we have no carbon, then the least electronegative atom is central. So do you think fluorine will commonly be a central atom? No, because fluorine's the most electronegative. Right? In our last compound, we didn't really have a central atom because there was just 2. But if no carbon, then the least electronegative atom is the central atom. And then the last rule is that hydrogen can never, ever, ever be a central atom. Hydrogen never, ever, ever can be a central atom. So let's think through why that's the case. Why could hydrogen never be a central atom?
Because it only needs 1.
Right. It only has 1 valence electron to give. So it can only be bonded to one thing. Okay, so you can write that down if you want to. Hydrogen only gets 1 bond ever. It never gets any electrons tacked onto it. It never gets anything else except for 1 bond. Okay? So hydrogen only gets 1 bond all the time. The bond is the 2 electrons, right, that it shares with something else. So hydrogen has 1 electron to give. So if I'm hydrogen and Allison's oxygen, right, she gives an electron, I give my only electron, and that forms a bond. And so I can't do anything else because I don't have any other electrons to give. That's right. It can only go to one thing one time, right? Okay. Step 3. Well, are we good with, do we have everything we need here? Step 3 is bond the central atom. I promise this will make more sense as we start making them, but you know, whatever. Bond the central atom to the outer atoms. And complete, sorry, I know you can't see this, complete the octets. Sorry. Okay. All right, we're going to try some here. I know this has been long. I'm sorry. That's just how it goes. Okay. We're going to first start with NH3. NH3. Writing in gray really bums me out. All right, here we go. NH3. Step 1 is to do what? Count valence electrons. So nitrogen gives us 5. Right? We got to be good with valence electrons. It's in the 5th group, or 15, so it gives us 5. Hydrogen each gives us 1, so 3, which means we have a total of 8 electrons here that we need to represent somewhere in our structure. Yeah.
So where did the 5 come from?
Nitrogen's in group 15 or 5 right here, so that means 5 valence electrons, right? 1 valence electron, 2 valence electron, 3, 4, 5, 6, 7, 8. Okay?
So if its thing was 2, then it would be 10. Like,
If it was N2, it would be 10 valence electrons for nitrogen, yeah. Yeah. Hydrogen is because each one is 1 times 3. Okay. So which of these should be our central atom? Hydrogen or nitrogen? Nitrogen, right? And then we say build our skeleton. So step 2 is build our skeleton. And so we know nitrogen has to go in the center. And so a skeleton means that we put nitrogen in the center and then we spread the 3 hydrogens out evenly around that.
How come nitrogen's in the center?
Hydrogen can never be in the center, ever.
That's just a rule.
Yeah, that's a rule. And if you're in doubt about what goes in the center, it's always the element that comes first. Okay, if you can't decide, it's the one that comes first. Okay, because we build molecules the least electronegative to most electronegative. So just go with that, right? And if you still can't decide, it's the one there's fewer of, right? You can't put 3 hydrogens in the middle and then 1 nitrogen on the outside, right? It would make the most sense to put the 1 nitrogen and surround it with your 3 hydrogens, right? So I've got my valence electrons. I've got my skeleton built. Next one is bond central to outer. So I'm going to say I use a bond, a bond, a bond. And so how many electrons have I used? 3 bonds, which gives me a total of 6 electrons, right? Each bond technically contains the electron from hydrogen and the electron from nitrogen. The electron from hydrogen and nitrogen, nitrogen and hydrogen, right? You don't have to draw the little dots as bond or as electrons. Maybe it just helps you visualize it for now, right? So I've used 6. I have 2 left. I have 2 electrons left I need to put somewhere. Can they go on a hydrogen? No. So they need to go on nitrogen, right? This is called a lone pair. Lone pair because it's not bonded. Lone because it's not bonded. Pair because there's 2 of them. Lone pair. That's how extra electrons travel in pairs. Yeah.
Okay, so you kind of just answered my question, but it has to be in pairs?
Has to be in pairs. So we don't put them like this. Right? That's no good. Got to be a pair. Okay? Uh-huh.
So I thought nitrogen couldn't get more than 1.
Nitrogen has 5 valence electrons, so it's going to use all 5 of those most of the time. Because remember, it's in group 5?
Oh, yeah.
So it's got 5 valence electrons on the outside. So if I were going to draw nitrogen by itself, its dot diagram would look like this. Right? And so I've used this bond to hydrogen, to hydrogen, to hydrogen, and then I've got my lone pair left over. Okay, do you see how that comes together?
Okay, wait, so if it's just nitrogen there and like there's no hydrogens around it, why is it okay to have like those 3?
Yeah, okay, so that's more than we need to get into, but it protects basically all of its sides first.
Okay.
Yeah, we won't ever draw individual elements. I'm just showing how it's got 5 to give, and it's going to spread them out. Mm-hmm. Yeah, you may, yeah. What did you say, Stephen?
Is it because like the positive ones and then the negative ones?
Not, kind of, yeah, kind of, yeah. We're not going to get into individual, electrons that are by themselves are called radical electrons, and we're not going to get into that right now. No. Okay, so now we count our electrons, right? We're going to count total. Does nitrogen have an octet fulfilled? 2, 4, 6, 8. Yes, nitrogen's octet is fulfilled, and we needed 8 electrons total. So that is a good Lewis structure. Right? That's it. Okay, let's try CCl4. Carbon tetrachloride. carbon tetrachloride. Step 1 is count valence electrons. Carbon gives us 4, because it's in group 4 or 14. Each chlorine gives us, bless you, 7, and there's 4 of them. So 7 times 4 is 28. So 28 plus 4 is 32 electrons. You will notice that there is never an instance in which our valence electron number should come out odd. Never will it come out odd. Okay, and I'll show you how we adjust for charges in a little bit, but never should it come out odd.
Where is the 7 from?
Chlorine is in group 7. It's a halogen.
Oh, yeah.
So it's group 17, so it's got 7. Okay. So 32 electrons, which is our central? Carbon. And then we go chlorine, 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 chlorine. Okay, so there's my skeleton. So I bond, 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 bond. How many have I used?
4.
Well, I've used 4 bonds, which means a total of 8 electrons. Right? Because there's 2 bonds, 2 electrons per bond. So 32 minus 8 is 24, I think. So what do we do with these 24 electrons? Yeah, we put them around the chlorine because carbon's octet is full. 2, 4, 6, 8 for carbon. There's 8 electrons surrounding carbon. So now I need to fill this chlorine's octet. 2, 4, 6. So now this chlorine's got 2, 4, 6, 8 surrounding it. So that means I've got 18 left. 2, 4, 6. I've got 12 left, right? You see where I'm going here? So now we check. We say, okay, is this chlorine's octet fulfilled? 2, 4, 6, 8. Okay, so that chlorine is good. 2, 4, 6, 8. That chlorine's good. 2, 4, 6, 8. Chlorine's good. 2, 4, 6, 8. This chlorine's good. Carbon's got 2, 4, 6, 8. So all of my elements, all my individual atoms have full octets. Now we count total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that is a good Lewis structure. All my atoms have complete octets. I use the right number. Okay. I'm going to give you, we're going to do one kind of challenge one, and then I'm going to send you one. Most of the time, yeah. Yeah, we talked about some that are exceptions, but for right now, tomorrow we'll get into a couple that have incomplete. But okay, I'm going to give you a little bit of a different one here. Ch2O. Ch2O. So the way that, okay, sorry, we'll do valence first. So carbon gives us 4, hydrogen 2, oxygen 6. So 12 electrons, I think, total. Okay. So the way that a compound is written gives us a clue as to its skeleton. So the CH2O means that these H's are bonded to carbon. And can the oxygen be bonded to the two hydrogens? No, so it's got to be bonded to the carbon too. And so when I draw my skeleton, I know carbon goes in the center. Right, it's got to look something like that.
Can the 2 hydrogens be above and the
Sure. Yeah, that part doesn't really make a difference for us right now. Okay, so I start my bonds. 2, 4, 6 electrons. I've got 6 left to go. Okay, so I should go ahead and fill around oxygen, right? So then I've used all my 6 electrons. Am I good to go? 2, 4, 6, 8, 10, 12. I used 12. What's the problem, though? Carbon does not have a complete octet, right? Because carbon only has 2, 4, 6 around it, and it needs 8. It needs 8. So what'd you say? Oxygen has 2, 4, 6, 8, because it gets to count part of that bond as part of its own. So oxygen's good, but carbon's not, and we don't have any more electrons to just do that, right? That doesn't work.
You can't move
You
the
just
bond.
double the
What I can do is I can go here and I can put in a double bond. Right? I take that lone pair from oxygen and I move it in to a double bond.
So then you erase the top two?
Yeah, then I take away those top and I move them into a double bond. So if I don't have enough electrons, I got to pull them in and I got to pull them into a bond somewhere, right? So now I check. Carbon's got 2, 4, 6, 8. That's good. Oxygen's got 2, 4, 6, 8. That's good. 2, 4, 6, 8, 10, 12 total electrons. Uh-huh.
So hydrogen doesn't need a full octet?
No, no. Hydrogen just gets one bond all the time. Yep, that's it. Good. Okay, questions about that? Okay. I'm going to talk to you just about some patterns that don't happen all